Okay, so today the topic is A/B testing, but I wanted to go over two main things that we're going to code out. So first, we're going to go back a little bit to power analysis, which is what we were kind of talking about yesterday, but I want to run through like a real concrete example for when power analysis is important. And then after that, we're going to go through an A/B testing example for real. So to get started, power analysis, some things to remember that within power analysis, this occurs before you actually conduct the experiment. And I'm going to set up this scenario in a little bit, but as we conduct the experiment, there are these four factors that have a strong relationship with each other. Sample size, effect size, your significance level, which is alpha, and power, which is beta. So all four of these very, very hand in hand. I showed you all this yesterday, I believe, that, if you want to solve for any one of these four, you can adjust the three and it affects the fourth. So for example, if we want to look at sample size and how sample size changes as we increase and decrease power, if we want higher power, sample size goes up. If we increase significance level, sample size should go up as well. Effect size, sample size should go down. So these are the things that are at play. All right, so let's set up this scenario. Let me just mute everybody before I start. All right, so let's set up this scenario. So in this example, we have a researcher who wants to study how daily protein supplementation in elderly will affect baseline liver fat. So the study budget will allow the enrollment of 24 patients. So here we already have our first constraint, our sample size, that we're constrained to only 24 patients because that's constrained by the study budget. So with these 24 patients, half will be randomized to a placebo group, and then half will get the protein supplement. They'll be part of the treatment group. And this trial will be carried out over a month. So it is desired to see whether the mean change in percentage of liver fat from baseline to the end of the study differs between the two groups in the study. So based on this, we know we're going to do some sort of two-sample t-test. So first, we know that we're constrained by our sample size first. So let's take a look at this setup. We have our hypotheses. Ooh, this says 0. This should be A. Okay. So we have our null and alternate hypotheses. So our null hypothesis is that the mean of the two groups' liver fat is going to be equal, meaning that, even though one group got the placebo, the other group got the actual treatment, their average liver fat is statistically the same. And alternate hypothesis is that they are different. We introduce another constraint here is that our alpha is going to be set at 0.05. So out of these four factors, we've set our sample size and we've set our alpha. All right. So here we have more context. The researcher needs to know what power will be obtained under the sample size restrictions to identify a change in mean percent liver fat of 0.17. So this is where we get our effect size constraint. And this is something that is determined prior to doing the experiment. If you think about it, let's say, I don't know what it was like actually, but when they were developing like the COVID vaccine, for example, and one way you can test for the effectiveness, I think, is you check for the number of antibodies, for example. I don't know how antibodies are measured, but for example, let's say you're doing a trial of these vaccines and you want to make sure that, okay, if the vaccine is effective, antibodies should go up by like 50%, for example. So you're setting that threshold for what counts as an effective amount of, I guess, an effect. So similarly here, they're saying that, okay, if we can get the average mean percent liver fat to go down or to change by 0.17, then that drug will be effective. So here we have our third constraint of our effect size. So for some more context, based on past results, common standard deviation of 0.21 will be used for each treatment group in the power analysis. So what we have here is out of these four, the first step we're going to do is try and figure out what's the power of this test with these constraints. So we have our sample size constrained to 24 or 12 per group. We have our effect size being the difference between the two groups is going to be 0.17. And we have our alpha at 0.05. So how do we set up power analysis? It's really through simulations. And so we're trying to figure out the power of the test, which is the number of times or the proportion of times where the null hypothesis is correctly rejected. So what we're going to do is we're going to set up these simulations, and there's quite a bit of code in it, but I'll walk through all of these. So we have our constraints, sample size of 12, 0.17 difference, and alpha. We want to find the proportion of simulations where the null hypothesis is correctly rejected. So how do we do this before we even conduct the experiment, before we even collect any data about any patients? At this point, we can just assume that we haven't even reached out to any patients yet. So let's set up some of our constants. So our sample size is going to be 12, and we're going to set up some parameters for each group. So first we have our control group, which for this case, we can use a mean of 0 and a standard deviation of 0.21. They did say that standard deviation of 0.21 is going to be used. Mean of 0, standard deviation of 0.21. And for the experimental group, we're going to use 0.17 because the change is going to be 0.17. And then experimental standard deviation is 0.21 because that's what they told us in the question. So let's just set 1,000 simulations. And what 1,000 simulations means is we're going to imagine that we have these two groups of people, one group that has these parameters and one group that has these parameters. What we're going to do is we're going to randomly pick 12 from each group, run a 2-sample t-test, and see whether the null hypothesis is correctly rejected or not. Because this group has a mean of 0.17, it is indicative of a difference. So you can sort of assume like, okay, before we even conduct this experiment, this group represents the group where there is an effect, and this group represents the control group. I think in the code, it will clarify a little bit more. Before we get into that, I wanted to show you all here. I have linked the t-test documentation. You literally just give it the 2 arrays of numbers, and then you can say whether it's a 1-sided or 2-sided test, and they'll do their t-test for you. So what's happening in this code here? First, we're doing a random seed. I don't think we've seen random seed yet, but random seed is actually something that's really helpful, especially over this next project that you're going to be working with another person. So a random seed is really for reproducibility. So how a random seed works is you can sort of think of it as it's like a function of the notebook. So if you set a random seed at the very top of the notebook, that random seed is set for the rest of the notebook. So you can see there are no like variables involved here at all. So before we get into the code, I just wanted to demonstrate what this does. So I have this random seed here, and let's say I have this code here. So actually, let me run this first, import our libraries, and run these constants. Okay. What this line of code does, and we're going to see it in a little bit, is it is going to randomly pick 12 points from a distribution, from a normal distribution centered at the control mean, which is 0, with a standard deviation of 0.21. So if I run this, you can see that I have 12 data points, very, very close to 0 because it is from that distribution. So because of this random seed of 10, every time I rerun this, I get the same numbers. Oops, I didn't mean to do that yet. But anyways, if I didn't have a random seed and I run this over and over again, the numbers change. Oh, let me just collapse this so it's not in the way. The numbers change every single time I rerun it. So this is helpful for just reproducibility. If you're doing any sort of random process in your project, you set a random seed, the number in the random seed actually doesn't matter. Feel free to look up how this works. It's actually pretty interesting, the concept of pseudo-random and how Python does it. Not the most important thing, to be honest, but good to know. You really just pick any integer you want. Let's say I put like 4, 5, 6. Every time I run it with 4, 5, 6, the numbers are just going to stay constant. So this just makes sure that you have the same subset of random every single time. So just in case anyone was curious about what this random seed is, because I think going forward, you're going to see quite a bit of this random seed thing. Okay, so what are we doing in this code? First, we set our random seed at 10. So I think this code actually does come from one of your labs. So if you run the solutions, and if you're ever doing anything where you find that all the code is the same, but why are my numbers not matching the solution? Make sure that you have a random seed set and it's set at the same integer value as whatever the solutions have. So what we're going to do is we're going to run 1,000 experiments because we set the number of simulations to be 1,000. We're going to run 1,000 experiments on hypothetical groups of people. So to store our results, we're just going to initialize an empty array. just to store it. So this part, you can technically append your p-values to a list, and we'll see that later. But first, this list, we're going to start with it as empty, fill it with NaN values first. For S in range and sim, so basically for 1,000 experiments, we're going to do this process. We're going to randomly sample 12 people from the control group centered at 0. And we're also going to sample 12 people from the experimental group centered at 0.17, and then run a 2-sample t-test between them. So as you can see here, I'm using the 2-sample t-test method, just feeding in these 2 arrays. And the result of this t-test, if you scroll down over here, it returns 2 things. It returns the t-statistic and the p-value, which for some purposes you might want to keep both. For our purposes, we only need to keep the p-value because we're just going to compare our p-value to our alpha. So what we're going to do here is we're just going to store all of our p-values. And we're doing t-test1 because this outputs a tuple, and we're just going to keep the p-value. So when we print p, let's see what this gives us. So when we print p, it actually starts out as an empty array, but now we have an array of 1,000 different p-values. And these p-values do differ. There's a good range. So for example, this first value over here is 0.23 because of the power of -1, 23%. So in this very first experiment, there's a 23% chance that these 2 groups are randomly different, or they are different just by random chance, I should say. Other examples, there are some other experiments where it's a little bit more significant. For example, there's this number over here to the power of -4. So in this particular experiment number, experiment number 12, you have a pretty high confidence that these 2 groups are different. So that you can see that there's a whole range of p-values here. So with these p-values, we just want to see what proportion of these p-values are under 0.05. Because all of these experiments, we technically should reject the null hypothesis because we are sampling from a population, this experimental population, we are sampling from a population that has this 0.17 difference. So there should be a difference detected. We just want to see how many of these 1,000 have correctly rejected this null hypothesis. So how we do that, we just figure out how many are below this, and then we get 0.495. So this is saying that out of 1,000 experiments, 495 of them correctly rejected the null hypothesis, which means that roughly half of these experiments that we did with all of these parameters set up of, sample size of 12, alpha of 0.05, and difference of 0.17, about half of the time, we're going to incorrectly make the conclusion that this drug had no effect when it indeed did. Does that make sense? Anyone need clarification on that? Okay, so prior to starting an experiment, this is how you can figure out the power of your test, which gives you a lot of good information, right? Like now that we know that half of the time with these constraints, half of the time we are rejecting that we are basically rejecting the drug when it actually did work. So instead, what can we do? Sometimes really depends on the context of the experiment, what you can change, but most likely what you would want to change, and the easier thing to change would be increase your sample size. So often you want to achieve a power of 0.8. This is just behavioral research. They usually want a power of 0.8, which means 80% of the time you are correctly rejecting the null hypothesis. So I want to show you all this pretty neat line of code. It's this solve power method from stats models as well. And this is pretty interesting. You basically give it any 3 of those 4 parameters and it'll just solve for the other one automatically. So what we can do here is let's just change this first. I think it's nubs 1 equals to 12, I think. Okay. So we're going to first instantiate this power. What that means, we'll get into that later. But we're just going to do solve power. We're going to use an effect size of 0.17 over 0.21 because effect size, if you remember, we have to normalize it based on standard deviation. That's just a formula that we talked about, I think, 2 study groups ago. Our alpha 0.05, our number of observations is 12. When we run this, you can see that our power that we got is 0.474. So this number of 0.495 that we got is just based on these 1,000 experiments. If we were to do this for more simulations, once we get to like about infinity simulations, that number will get closer and closer to 0.474. So this solves it exactly for us. So, okay, cool. Let's just say that we can increase the number of observations. What is the number of observations needed to get a power of 0.8? So let's undo this, and it'll just tell us straight away. When I run this, it'll solve for the number of observations that we need to have in each group, and that would be 24.95. So what that is saying is that we need at least 25 subjects per each group in order to achieve a power of 0.8. So this is something that, I don't know, really depends on context, whether they have the budget to have more patients or not. Maybe they just want to see hypothetically how many would we need. You can give them that calculation just like this. Questions? Cool. Alternatively, you can also do this iteratively. We can basically repeat this process, but for increasing sample sizes. So this code, honestly, not very important because you can really just use this one line here, but I just want to demonstrate. This is really just the same code as what we have above, just scaled up. And what we're going to do is we're going to see whether as long as the power is below the target, we're going to increment our sample size by 1. So here we're starting our sample size at 12. You can see our sample size increments by 1 each time. Let's just run this code. I don't think it's important to go through exactly what each line means. If anyone has questions, feel free to ask during a one-on-one. But as we run this, you can see that as we increase the sample size, the power slowly goes up. And then at a sample size of 25, that's when we achieve our 0.8 power. And then you can also take a look at this graph to just plot power versus sample size. I will say, if you were ever asked to calculate the power of a test, you can definitely use this line in practice, but I guess also good to know. If I were to set the target to be higher, let's say I wanted to see, I don't know, 0.95 power, what's my sample size in order to achieve a 0.95 power? Run this again, you can see that I need 41 samples in each, 41 observations in each sample. Run this, you can see that this power curve is going to actually slowly plateau out. So cool. Any questions relating to this power versus sample size, or basically power analysis for an experiment? All right, okay, so that's the first thing I wanted to talk about. The next thing that I'm going to code through is an A/B testing example. And this is also from one of your labs, but there are just a couple of things that I wanted to mention in terms of like, some of the code is a little bit, I think, new. So I want to talk through some of that. I will say, out of all of the things that we talked about so far, the most likely application of statistics directly is in A/B testing. So I've actually had a few students who have had like take-home interviews or interview assignments that are literally just, this with different data. So this is actually a really good one to familiarize yourself with. So this data is basically a bunch of actions on a website. And so the context, it sets it up better in your lab, but just imagine that you have a website and you want to get people to click on something more often. So they're A/B testing something like a new feature on their site. And they want to see whether this new feature leads to clicks or not. In order to fairly test the effect of this new feature, you are only going to give this new feature to some of your audience. Not everyone who goes on your site will get this new feature. Let's say around half of them will. So we're going to see between the half that gets this new feature and the half that doesn't get this new feature, is the click rate different? So this is an example of what some of the raw data can look like. You can see that this is timestamped. And if you ever get like website information or data that's collected, I guess over time, you often have like data that looks like this, that is not aggregated in the best way, but we're going to see that process in a little bit. So you can see there's a bunch of different user IDs here. And some of them are assigned to the experiment group, some are assigned to the control group, and you see what actions they take. And in this case, there are only two possible actions. You either view the page or you click on the page, on the thing on the page. So what we have here, I just want to point out that there are multiples for some IDs. So you can see here, we have 2 rows of this ID number. Let me just zoom in a little bit. And you can see like within about 40 seconds, the person viewed it and then clicked. And this person happened to be in the experiment group. Another example here, also the experiment group, in about a minute or so, viewed it and then clicked it. So there is quite a few of these, and not all of them are from the experiment group, as we will see in a little bit. But we basically want to see, is there a difference between the click rates of the experiment group and the control group? Okay, so let's just do a very, very quick EDA. All this code is, you can look through it on your own, but number of viewers, 6,300, number of clickers, about 1,800, number of viewers who did not click, 4,400, and this makes sense, number of clickers who didn't view, 0, because you cannot click on anything if you didn't view it. So, okay, these numbers kind of check out. In terms of setting up your data, later we'll see what kind of format we want the data to be in order to conduct this t-test, but there are different ways you can go about this data cleaning process, and this is just one of them. So in this process, which I did take from the solutions, they split up the 2 data frames into the control and experiment group, such that this experiment data frame only has people from the experiment group, and the control only has people in the control group, just so you can have them as separate arrays later on. What they do here, and you'll sort of see they do a pivot table as well, and I'll show the result of that too, but they add this count column at the very end just so that you can sum up values more easily later. So they're just adding this count column to help with aggregation in a little bit. All right, so this pivot table, feel free to like break down this code on your own, but I just want to show you all what the result is. This is the result of doing the pivot table. So this is for, let's see, this is for the control group. For the control group, now you have each ID as an individual row, and you have sort of like binary variables for whether the person clicked or viewed. So views should all be 1s, but click, you have 1s or 0s, depending on whether they clicked or not. So from this, you can get your click-through rate, basically. So here you can see that in your control group, we had 3,300 people. Experiment group, we had roughly 3,000 people. And the total clicks, 932 from the control, 928 from the experiment. And the average click-through rate that we want to compare the difference of, control had a click-through rate of about 28%. Experiment group had a click-through rate of about 31%. So what are we trying to do here? We want to see whether this difference in about 3% of click-through rate, is this statistically significant or not? Is this difference of 3% between the 2 click-through rates between like the control and experiment group, is this statistically significantly different or not? So there are all of these formulas from the old labs, which I will just use just to show you all how they work. But this is going to run a Welchs Ttest because if you remember, we talked about Welchs Ttest at the beginning of yesterday. Welchs Ttest is just same as the t-test, except for it accounts for different standard deviation and also different sample sizes between the 2 groups. So because these groups are slightly different, we're going to use a Welchs Ttest. So these are just the formulas for conducting the Welchs Ttest. You get your t-statistic with this formula, you get your degrees of freedom from this formula, and then you actually conduct the test here. Now, this is here if you want to use it. I think in the labs, they actually have you code these out. I honestly don't think it's as important because we have that one-liner that we can use out of stats models. Unless you really want to go and become a statistician, you don't have to know this, really. Yeah. Okay, so let me just run these functions so that we have them. And I'll just show you all the kind of data that we want to feed into our, into the t-test. We're going to feed in control.click and experiment.click. So what that looks like is basically a bunch of a series of 1s and 0s based on click or not click. So that's what we're going to feed in here. So control.click is the same thing as doing control click because it's just the click column of the control data frame, and save for experiment. So we just want the 1s and 0s of whether they clicked or not. And then for this case, we're just going to assume that it's a 2-sided test. If it's not a 2-sided test, you'll get a different p-value. So this is using these defined functions. And so when we run this here, we get a p-value of 0.008. So there's only a 0.8% chance that this difference was just randomly observed. So we can pretty confidently say, especially because we had our alpha set at 0.05, that there is a significant difference. So this 3% difference in the click-through rate is statistically significant. That's great. So just to show you all, using this t-test formula that, the t-test method out of stats models, we get the same result. So by feeding the same data as well, slightly different, you can see that it's still about still 0.008. So about the same value. There's just some rounding error in here. And you also get your t-statistic out of here. So going back to what we had earlier, if you want to get only the p-value, you can do this to get just the p-value. Now, if this wasn't a two-sided test, oops, I think you do this, you get a p-value of 0.044. And just to demonstrate how we use this, I want to say it's alternative. And I think if you do less or greater, I forget, okay, less, then you can see that our p-value is halved, because in this case, if we are checking to see if the click-through rate is greater or lower than, I forget the direction of, it depends on which one you give first, but yeah, we can also do it as a one-sided test, just like this. But yeah, the main thing I want to take away from here is when you're given an A/B test data set is not always so straightforward the way that you need your data to be in order to fit it into your t-test function. So just be aware that you need your data to look something like this in order to run the t-test successfully. But yeah, typically if you do get this in an interview, they will expect to see some EDA, probably more comprehensive than this. A lot of times you are given like other information about users as well. Maybe you can plot like the time that people are looking at the website. So just for your information. But yeah, we finally got back to some coding. Any questions? This is kind of all I had to share for today. Questions? Awesome. Cool. So make sure that you've heard from your project partner by this point. If you haven't, please let me know. If you're trying to think, what should I be doing now? I would say now is a good time to take a look at the data set or source your own data set. And again, reminder, if you're sourcing your own data and you've picked one, please let me know what it is so that I can approve it first, just so you don't go down any rabbit holes that you shouldn't be going down. So yeah, let me know if you haven't heard from a project partner yet. And yeah, it's a good time to start looking at your data set, do some very like overall EDA, maybe plot some graphs based on what you have. Next week, we're going to get into more direction of like what kind of EDA is useful, but it's still a good idea to familiarize yourself with the data that you're going to be using. All right. Well, if there's nothing else, tomorrow we're going to get into a little more conceptual stuff. I'm going to go over the process of solving a probability question. And then I'm going to talk about what is known as maximum likelihood estimation. I will preface that by saying that MLE is a very abstract mathematical concept, but it's quite important to modeling. So right before we get into our linear regression next week, I do want to start with that. So yeah, there's no material on that on the repo, but I'm just going to be like writing and drawing stuff out on my tablet. You'll see that. Cool. Any final questions before we close out for the day? Going once, going twice. All right, well, have a good Thursday, everybody. I will see you all back here tomorrow at the same time. By the way, I don't post the Zoom link in the Slack channel too much, so just remember to come on here at 2 p.m. Eastern. So yeah, any other questions that you all have, feel free to Slack me, but if there's nothing else, I will talk to you all tomorrow at this time. All right, bye, everybody.